Hello again, this is Miss Nakayama. Today's lesson is 3.2 Logarithmic Functions. Happens to be one of my favorite things to talk about. I love logs. But let's look at all the stuff I'm going to talk about in this video. First off, we're going to change between logarithmic and exponential, backwards and forwards. Then we're going to make sure that we know how to evaluate logs. We're going to use basic log properties. We're going to graph logs, find the domain of logs, and then use common and natural logarithms. Okay, so first of all, what is the definition of the log? Okay, in the last video, I talked to y'all, we looked at the exponential function, and we looked at an example, y equals 3 to the x. We looked at lots, but y equals 3 to the x. And one of the characteristics, if you don't remember, was talking about the inverse of it. And if I asked you to find the inverse of this function, that means that you're supposed to switch the x and the y variable. That's how we find inverses. So if I were to switch them, then I would have x equals 3 to the y. Well, and if that was the first step in finding the inverse, and after that, you were supposed to solve for y. And we don't know how to solve for y. So they came up with the log, and they came up with a way to rewrite that thing. So what it says is that y equals the log base b of x, and that's equivalent to b to the y equals x. Okay, the main thing that you really want to remember is that the log, y'all, is just a fancy way of asking or giving the exponent on a function. Okay, look right here. This right here, this y, it says it's the log. Well, where is that over here? It's the exponent. Okay, I'm going to talk about that a lot as we go through here. Okay, we've got to be able to go back and forth between these two expressions because they are equivalent. Okay, so one way that some students find it easier, if the log is written on the other side, if the y, is written on the other side, you start with the base that's down here on the bottom, and they call it the kick out because they say b, and then they go to the y is equal to x. And so it looks like that, b to the y equals x. Back and forth between those. But if the y is on the right side of the equation, it's a little bit easier than it was if it's up here. Okay, so some examples of that. Changing from logarithmic to exponential. As I said, it's a little bit easier if I take this and move it over here. So I move it over there, and then I'm going to say, okay, what is that going to be? Well, when I do it, 7 to the third equals x. So that looks like that. Again, I'm going to take the 2, and I'm going to move it over here. And I'm going to start at the base to the 2. That 2 is the exponent, is b squared is 25. That's what that is. So the exponent in my exponential, okay, is the log. The other thing that's really key, y'all, is that the base in the exponential function is the same as the base in the logarithmic function. My base is b, my base is b. So it's another way to help you keep things straight. 4 to the y equals 26. So 4 to the y equals 26. Now, go the other way. A little bit more challenging, but you can always check yourself. Okay, so when I do this one, I have to rewrite it as a log function. 2 to the 5th equals x. Remember, I told you the base stays the same. So the base is 2, and the exponent is the log. So the 5 is going to go over here, and my x is going to go there. What's left goes there. And you can check it out. 2 to the 5th equals x if you do the little kick out we did. All right, look at this one. My log is, what is the base of my exponential? The base of my exponential is b. The exponent is 3. And so 27 is going to go here because that's what's left. Okay? Again, my base is e. My exponent is y. And so 33 goes here. And that's what my expression looks like. Again, easy to check. Okay? So look at these evaluating logarithms. They tell you to do it without a calculator. If you learn how to do it without a calculator, that's why I keep giving you the examples in the daily check-in, because it's going to make your life easier. Okay? But what you're thinking of when you're evaluating logs is, what is the exponent what's the exponent on 10 to make it equal to 100? Well, y'all already know. That's 2. Okay? What is the exponent on 5 to make it 1 over 25? Okay? Well, if you know that, well, let's put a pen. 5 to the third is equal to 125. How do I make it a fraction? Is I need the negative exponent. So the answer is -3. What is the exponent on 36 to make it 6? Well, that's a square root, and the square root written as a fraction is 1/2. 36 to the 1/2 power is equal to 6. Put it in your calculator, check it out. Log base 3 of the 7th root. What exponent makes 3 that? Well, the 7th root is the same thing as 3 to the 1/7. So what is the exponent? It's 1/7. That's all it is. All right, basic log properties that you want to be familiar with involving the number 1. First off, whenever the base, okay, if this base down here, these two numbers are the same, it's going to be 1. That's what that little 1 is, because it's still the exponent, as I mentioned. And the other thing you need to remember is that log of 1, no matter what the base is 0. So look at these examples. Okay, log base 9 of 9. Those bases are the same. There's an exponent of 1. That answer is 1. Okay, what is the log of 1? No matter the base, it's 0. 52 and 52 are the same. It's 1. Log of 1, 374, the same. Log 1, doesn't matter what the base is, it's 0. Okay, now, I already mentioned to you about inverse properties. Okay, so when we compose inverse properties, I know y'all are loving to hear this part, but when you compose inverse properties, f of f inverse of x is equal to x. And it doesn't matter which one, f inverse of f of x is equal to x. What you have to be familiar with, what does that look like in regards to exponents and logs? The first one looks like this. The log base b of b to the x. That's what I was just doing with the number 1. X was 1 back then. Okay? But the key is when these two numbers are the same, it's whatever the exponent is, because the log is the exponent. Taught out of a book that called these White House. What color is a White House? I think y'all know it's white. So that's if you start with the log. If you start with an exponential, it looks like this when you compose them. So I have b raised to the log base b, but again, the base of my exponential and the base of my log are the same. So it's kind of the odd man out. So look at these examples here. Okay, evaluate. Okay, again, y'all, if you get this, it's so much faster than to do it without a calculator. Okay, log base 7 of 7 to the 8. These are the same, so my answer is 8. 3 raised to the log base 3 of 17. These are the same, so the answer is 17. Log base 52 of 52, answer is -3. 5 raised to the log base 5 of 82. It's the odd man out. That's all. What color is the White House? Running out of room here. Log base 374 of 374 to the x plus 2. X plus 2. 9 raised to the log base 9 of c minus 4. C minus 4. Bad example they gave you. Should have. No, it's in the exponent. Doesn't matter. Okay. So those things are going to be very helpful when you get into solving equations. Okay. So it is important to recognize that. All right, graphs of exponentials. I'm not going to spend a lot of time. I'm going to do the examples, but I just talked to you at the beginning, okay, about these two being inverses of each other. Okay, the log and the exponential. How are they related to each other? They are inverses. So notice that every x value that I have over here is a y value over here when I plot. Okay, and similarly, my y values, my y values that are here are my x values over here. All right, the exponential is increasing still. If b is greater than 0, we're going to talk about that. Logarithmic is also, but each of these points has just been flipped to get 1. I've got 0, 1 on my exponential. I'm going to have 1, 0 on my logarithmic. So if you know one set of points, then you know the other set of points because you just flipped them. All right, so you do have to know the characteristics, but the characteristics, again, if you know the characteristics of the exponential function, you know them of the log because they're that closely related. So if you remember, the domain of every exponential function was negative infinity to positive infinity. Well, that means that's the range of my log function. And the range of the other one was 0 to infinity, so that's my domain. Okay, they just got flipped. Okay, I just told you on the graph, we had the point 0, 1 on the exponential. Now we're going to have the point 1, 0. Before we had no x-intercept. Now we're going to have no y-intercept. Okay, if b is greater than 1, it will be increasing. If b is less than 1, but always greater than 0, it will be decreasing. On the exponential function, the x-axis, or y equals 0, was our asymptote. Now we're going to have the y-axis, or x equals 0, and it will be a vertical asymptote. And I do tell people, I hope that you will remember, but this is the log function. So y equals log of x. Well, that first letter in the word log is your vertical asymptote. So you can remember when you think about the log function, this right here shows you that vertical asymptote. Okay, so one of the other things that's important to remember, okay, because the domain and the range got switched, my domain is all positive numbers. I cannot take, it's all positive real numbers. I cannot take the log of a negative number, ever. So you've got to remember that whenever, and this is really, really important, but whatever this is cannot be negative. It's not defined. So you take that part of the log function and you make it greater than 0. Can't take the log of 0 either. Okay, 0 is not positive, so that's why it has to be positive numbers. Solve for x, put it in interval notation, and that is our domain. It's as simple as that. Take the argument. What I highlighted in yellow was called the argument. Make it greater than 0, solve for x, put it in interval notation. Here's the graph. Okay, so that you know from your transformations that the graph has been shifted to the right 5 units. Well, my asymptote went from x equal to 0 to x equal to 5. So our asymptote will only change if there's adding and subtracting inside of the parentheses. Again, if it affects the x, it'll be inside the parentheses. So look at something else before we talk about the graphs. You've got to know that if a log has a base of 10, it is called the common log. Normally it would be written like that, but you will not see it like that. You've got to understand, remember, if there is no base down here, it's understood to be 10. It's called the common log. It is a button on your calculator if you want to use it. Okay? Most importantly, look at what these inverse properties. I already talked to you about this right here, composing the inverses. This is what it looks like. Log base 10 of 10 to the x. Those bases are the same. 10 raised to the log of x. It's equal to x. Okay? All right, that was common logs. Common logs have a base of 10. Natural logs, we talked about this yesterday, have a base of e, called the natural logarithmic function. You could think of it as log base e of x, but it's not written like that. It's written ln of x. So you have to know that ln of x means the natural log. And this, more importantly, are its inverse properties. ln of e to the x. So those two things right there have the same base. And e to the ln of x equals x. Again, same base. Okay? So look at these using our inverse properties. Okay? Log base 10 of 10, that's that same thing I was doing earlier. Same base. The answer is negative 3. Same base. The answer is 82. Same base. ln of e is the same as log base e of e. So I get to take just the exponent. e to the ln of 2x, those again, same base. Okay, look at this one down here. Little bit challenging, so you might think about writing it as, instead of 1 over e to the 13th, that is the same thing as e to the negative 13th. So now when you cross them out, I have an answer of just negative 13. And again, e to the ln of 4x to the third, same base. So I'm composing inverse functions, and I get the odd man out. All right, graphing, just to review, same thing we did yesterday, okay? We have to determine the characteristics, and then we're going to have to answer those questions. So g of x equals log base 4 of x plus 8, okay? X plus 8 is a shift opposite. It's inside the parentheses with the x, so it's going to shift it left or right. Does the opposite of what it looks like, so it's going to shift left, which means my asymptote is not x equals 0, but x equals 8 to the left, which is negative 8. And my domain is always tied to that asymptote. If you remember our exponential function, the range was always tied to the asymptote. Well, this is x, y'all. So x goes with the domain. So the domain and the asymptote are tied together. So negative 8 to infinity, and the range here is always negative infinity to positive infinity. Okay? ln of 7x, again, affects the x. It's multiplying, but because it's the x, I'm going to do the opposite. So instead of stretching it, it's going to shrink it horizontally, which is what letter? It's letter I. So my asymptote, I did not add or subtract inside there, so my asymptote doesn't change. Domain and range don't change. Okay, log negative 3 times the log base 5 of x. So this right here is the parent function, y'all. So you have to identify all of the other changes in there. The reason, well, I'll go through it step by step. So the I is not, and as I said, y'all, if it affects the x, it's in the parentheses. None of these are in the parentheses, so they all affect the x. They all affect the y. So they do the same thing. So the negative means it's going to reflect over the x-axis, which is h. The 3 is going to stretch it vertically, which is b. And the minus 4 is going to shift it down, which is e. Okay? Again, no change to the x, so my asymptote doesn't change, and neither do my domain and range. And then the last one, g of x equals the log of x minus 3. All right, that 3 is inside the parentheses, which means, and it's a shift. We do the opposite. So instead of going minus 3, I'm going to do plus 3, which means I'm going to the right. And a shift right is j. And that affects my asymptote. So now my asymptote is x equals 3. Domain is tied to the same thing. And my range is the same. All right, I got 2 word problems, and then I think we're done. So first off, the percentage of adult height attained by a boy who is x years old can be modeled by f of x equals 29 plus 48.8 log of x plus 1, where x represents the boy's age. So we're going to pay attention to those labels. And f of x represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at age 10? So I'm looking for the y. Age 10 means x equals 10. So I'm going to go calculate f of 10, which means I'm taking this lovely equation here, and I'm plugging in 10 for x. Put that on your paper so you can get partial credit if you mess it up in your calculator, but you should practice. Put that in, make sure you know where your log button is, and you get 79.8. Approximately what percent? I'm going to round that to 80%. All right, last problem. Whoops. When the outside air temperature is anywhere from 72 degrees to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function below, okay, models the temperature increase f of x in degrees after x minutes Use the function to find the temperature. So I'm looking for y, f of x, after 30 minutes, which means that x equals 30. So I'm just plugging in 30 wherever I see x. Plug that in, put it in your calculator. 33.98 round to the nearest degree is going to be 34 degrees. So that is all that I have. Not really all, but that's where I'm going to stop this video talking about logs. And I thank you so much for watching. I hope you got a lot out of all the examples. If you have any questions, please don't hesitate to email me or come see me. Thank you so much for watching, and y'all have a great day.